Let's first look at some examples of self-inverting integers. Now, in the real number system, the only self-inverting number is 1 itself, okay? But there's a lot, it's a broader concept in modular arithmetic. So let's look at 10 squared. It's congruent to 1 mod 11. And you know what that means is when you subtract 1 from 10 squared, you get 99, which of course is a multiple of 11. So 10 squared, 10 would be an example of a self-invertible integer. Notice it's equal to p minus 1. Now another example would be 21 squared. Notice we just bumped up by a multiple by 11. 21 squared is also congruent to 1 mod 11. Now 21, if you need to do the computation, it is because it's congruent to 10 basically. But if you don't trust that and you want to do the computation, 21 squared minus 1 is equal to 440, which is clearly a multiple of 11, right? Okay, so that would be congruent to 0 modulo 11, right? Okay, 21 squared is what, 441? Yeah, 441, so I think I got that right. Okay, so both of these are examples of self-inverting integers, modulo 11, and of course you have to mention the modulus for the whole concept of mean anything. Now the rest of this is just an algebraic exercise, and we can verify these two numbers once we're done with this. We're given that A and B are self-inverting, and so that of course means that A squared, and just for shorthand I'll write it like this, A squared comma B squared, okay, is congruent to 1. Lazy man way of doing this thing. Is congruent to 1 mod P. Okay, so the rest of this is just some knowing the binomial expansion. Okay, so let's go down and do the binomial expansion right here. So we get A plus B quantity cubed. All this is very well known. And you can see I write this out in a way that's probably a little puerile, but you can see right here I have an A squared which became a 1. Now here you had an A squared which became a 1, and so we just left the 3, right, and the B. In a similar fashion here we leave the A because B squared is also self-inverting. Okay, and so you get this fairly quickly. It's equal to 4 times A plus 4 times B, and of course you can distribute and write it this way. And so we have reduced this entity A plus B cubed down to a simple linear expression. Again, it relied heavily on the fact that the elements were said to be self-inverting. Now let's take a look. What did we use a while ago? 20 and 10, or 21 and 10 were shown to be self-inverting. Okay, so right here you could go 21 plus 10, right? So that would be 31 cubed, right, folks? Again, I'm using A equals 21 and B is equal to 10. So, are those numbers? Yeah, 10 and 21. Okay, so we were checking to see if 31 cubed is congruent to 4 times, and that, you see, this is pretty easy to see, right? 4 times 31. Now again, I'm positing this as a question, but it's clear just manifestly here you can, we're talking mod P of course, but you see how if you could rewrite this is 31, you can factor out a 31, right? So you would 31 and then subtract, you would have 31 squared times 31 minus 4. Okay. Now, of course, I just brought it to the other side, right, folks? So that's congruent to 0 mod 30. Or let's see, wait, what are we doing here? 21, 31. Did that work out for us? 27, we need, P is 11, right? Yeah, that's modulo 11. I'm not seeing it right off the. See, this would be 27, right? Huh. I thought it'd be easier than that. 31. Well, it's just clear that 31 divide. Yeah, if you factor. Huh. Okay, y'all, I'm not seeing it right here. I'm not. I gotta go do something. But this didn't prove anything right here for the special case. Let's just check real quick. This is certainly true, but I haven't really shown it to you. Let's see here for this special case. We're doing A equals 10 and B equals 21, and so this would be 31 cubed is congruent to 4 times 31. So 31 divides. Okay, well, an easier way to look at this probably is true, but I didn't show you. This, you can think of, oh, my bad. This would be, you can only take out 31, right? You can just take out 31, then this is 31 squared minus 4. It's still not clear that that's divisible by 11, though, is it? Okay. But anyway, the identity, it is. You can check it. I'm not showing it numerically here for you. But according to this identity, this has to be true. But I'm just not getting it done here. Let's see, 31. Anyway, I won't hold you up any longer. But anyway, this is the point where you would say QED. And you may want to check with smaller numbers here. It's probably right in my face. I'm just not noticing it. But it's QED time right here. Try with a smaller, like 1 and 4. 1 and 4 are self-inverting, and you would get 5 cubed. Yeah. If you do 1 and 4, that's a little more clear, mod 5. And I think here, I guess you just got to do a computation, right? 31 squared minus 4. Yeah, as far as I know. Who knows? But in any event, that does it. I think this was just wrong to try to do it algebraically. But anyway, we're done. I'm done with the video. Hope it made sense to you. And I like this idea of self-inverting. It's something that's used to help prove Wilson's theorem. Okay, since 1 and p minus 1 are self-inverting, and then everything else has multiplicative inverses, and so you'd end up getting Wilson's theorem out of that. Okay. All right, that is all, folks. Thanks for viewing.